Welcome to this explainer from the E3 Nexus Lab. We're all about exploring the intersection of energy, the environment, and, well, electrochemical interfaces. So let's dive right in. The world is going electric. Everything, our cars, our homes, our entire grid. But what's going to power it all? The answer, you guessed it, lies in the future of the battery. So check this number out, 100 terawatt hours. That is a staggering amount of grid storage the world might need by 2050 if we're going to fully transition to renewable energy. And get this, that's just for the grid. If you want to electrify every single car on the road, you can go ahead and add another 144 terawatt hours on top of that. I mean, the scale of this challenge, it's just mind-boggling. And here's the core of the problem, right? We call it the intermittency problem. On one hand, you've got your renewable supply, solar and wind. And that stuff fluctuates. The sun doesn't always shine, the wind doesn't always blow. But on the other hand, our demand for electricity, it's constant, 24/7. This mismatch creates what we call multi-day gaps, where the supply just can't keep up. So to keep the lights on, something has to fill in. And that something has to be batteries. Okay, so when we think about solving this, where does our mind immediately go? Well, we naturally turn to the hero of the modern energy story, the lithium-ion battery. I mean, think about it. This is the technology that cut the cord on our phones, it's what's powering the entire EV revolution, and so far, it's been the go-to choice for grid storage too. And a huge, huge part of its success comes down to this absolutely revolutionary cost decline. Seriously, look at this. Back in 2010, just a little over a decade ago, we're talking over $1,000 per kilowatt hour. Today, we're hovering somewhere around $100. That incredible price drop, that's been the single biggest reason it's everywhere. So yeah, for these short duration jobs, balancing the grid for a couple of hours or powering your daily commute in an EV, lithium-ion is the undisputed king, no question. Which leads to a pretty important question, right? If it's so great, why are we even talking about needing anything else? Well, here's why. For all of its incredible success, lithium-ion is starting to hit a wall. It has some really fundamental limits, especially when you start talking about that colossal job of storing energy, not just for a few hours, but for days at a time. And this really is the ultimate test. You see, the technology we use right now to fill in those multi-day gaps, it isn't another battery. It's a natural gas power plant. So, for any new battery technology to win that job, it has to do one thing. It has to beat natural gas on cost, period. And here's the tough reality of that. To be cheaper than a gas plant over, say, a 100-hour gap, an installed battery system needs to cost less than $20 per kilowatt hour. But with lithium-ion, look at this. Just the raw materials inside the battery, the cathode, the anode, the electrolyte, that stuff alone already costs more than double that target. There's a fundamental cost floor here that it just can't seem to break through. But it's not just about cost. Lithium-ion is hitting a second wall, and this one is all about geopolitics. You've got these key materials like cobalt that aren't just expensive. The bigger problem is that their processing is incredibly concentrated. When you see that something like 70% of all cobalt processing happens in a single country, well, that creates a massive supply chain risk for a technology that the entire world is banking on. This brings me to one of my favorite quotes from Professor Donald Sadoway at MIT. If you want to make it dirt cheap, make it out of dirt. And that just perfectly sums up the philosophy we need for the next generation of batteries. I mean, if you want to solve a planetary scale problem, you have to use planetary scale resources. You got to build these things out of materials that are abundant, cheap, and you can find them everywhere. And that philosophy, it brings us to this whole new class of technologies. These are batteries designed from the ground up, specifically for low-cost, long-duration storage. Think of them as the grid-scale workhorses of the future. Let's take redox flow batteries, for example. What's so cool about these is that they completely decouple the power from the energy. Your energy is stored in these liquid electrolytes, basically held in big, simple tanks. So if you need to store more energy for a longer time, you don't have to redesign the whole thing. You just build a bigger tank. It's a really elegant and simple design that's just perfectly suited for affordable, long-duration storage on the grid.
And there are other amazing concepts out there, all using some of the most common elements on Earth. You've got iron-air batteries, which, get this, they literally breathe. They pull in oxygen to basically rust iron, and then they breathe out to reverse the whole process. Or how about liquid metal batteries? These things have 3 liquid layers, 2 different metals and a salt in between, and they just self-assemble based on their own density. No membranes, no fire risk, just simple, scalable, and literally made from dirt.
Okay, but it's not just about long-duration storage for the grid. That's a huge piece of the puzzle for sure. But there's a whole other frontier of battery research that's focused on creating technologies that can actually improve on lithium-ion's core performance for things like our vehicles and maybe even aircraft. Lithium-sulfur batteries are a really compelling example here. They are extremely lightweight and super powerful, and they use cheap, abundant sulfur, which is literally an industrial waste product, and pair it with a pure lithium metal anode. This combination could be a total game changer for applications where every single gram counts. Think long-haul trucks or, yes, even electric aviation. And then there's what a lot of people in the field consider the holy grail of battery research: solid-state batteries. The key innovation, the big idea, is to replace that flammable liquid electrolyte you find in today's batteries with a solid, non-flammable material, something like an ultra-thin layer of ceramic or a polymer. Now, this one change, it's a massive unlock. First, it makes batteries fundamentally safer. You're getting rid of that fire risk. Second, it lets you make more compact designs, which boosts energy density. And third, and this is critical, it finally allows for the safe use of a pure lithium metal anode, which can pack way, way more energy than the graphite we use in anodes today. So, after all that, what does this actually mean for the future of the battery? Well, I think the most important thing to take away from all of this is that there's no single magic bullet. The idea of, one battery to rule them all, that idea is quickly fading away. The future isn't about one battery versus another. It's about building a portfolio. We're shifting away from this one-size-fits-all approach that we've had with lithium-ion and moving toward having a diverse toolbox full of specialized technologies. So you'll have those long-duration workhorses for the grid, you'll have high-performance batteries for EVs, and you'll have those ultra-lightweights for aviation, each one designed and perfectly suited for its specific job. But look, inventing these new technologies, that's really only half the battle. As Professor Sadoway points out, these really radical new chemistries, they're probably not going to come from the big established industries. They'd almost always come from universities and startups. And that means getting them from the lab to the market requires a completely different kind of thinking, a different kind of support, and a different kind of investment. And that leaves us with a final, really crucial question. The science is here. These new chemistries are emerging from the labs as we speak. But do we have the collective will to actually build the massive, sustainable, and ethical supply chains and manufacturing facilities to bring them to the incredible scale that's needed to power our future? Thanks so much for watching. If you want to keep exploring the future of energy and the environment with us, be sure to subscribe to the E3 Nexus Lab channel.